Today we're going to start Chapter 7, Section 1, and we're going to be using fundamental identities. Now, the fundamental identities that we're going to use are going to be the same ones we've seen before. Now, the first ones are the reciprocal identities, and everybody should realize that the reciprocal of cosecant is sine, reciprocal of secant is cosine, reciprocal of cotangent is tangent. The other identities here, the tangent x equals sine x over cosine x, and cotangent equals cosine x over sine x. These were labeled before as our quotient identities. Now, we saw them before, but we never had to use them. And then the other identity that we've had to use before are these Pythagorean identities. Now, these other two categories here, the even-odd identities and the cofunction identities, we're not going to use them. They are listed in our textbook, but we're not going to cover those. You will cover those in your pre-calculus class. So the ones that we're going to focus on are the ones we've already seen before. Now, one other thing that you should be able to do, or maybe even have a list of ahead of time, is be able to manipulate these Pythagorean identities and solve for any part of it. So what I mean by that is, let's say we take sine squared x plus cosine squared x equals 1. And let's say instead of seeing it in this format, let's say I tell you, solve this thing for sine. So what we would do is we would subtract cosine x, cosine squared x. And let's say I just want to make it so that sine squared x is all by itself. Because what we're going to be doing in today's lesson is a bunch of substitution. So for example, let's say you have sine squared x in your problem, and you want to get it to have a bunch of cosines in it. What you can then do is take what sine squared x equals, which is this, and you're going to substitute it. So be able to solve any of your Pythagorean identities for any of the different parts. I could have even taken that same identity and solved it for cosine squared x. So be able to rearrange it and turn it into any rearranged combination, but it still means the same identity. So if I wanted to solve it for cosine squared x, instead of now subtracting cosine, I subtract sine. And now I get cosine squared x equals 1 minus sine squared x. So be able to manipulate them. Since it's open notes, maybe have them all rearranged ahead of time. So that way when you go to take the quiz or the test on this, you don't have to waste time doing this. And you'll be able to say, oh, here it is, I'm going to use that one. And it'll make it a little bit easier. Now, our goal here is going to be simplifying these trig expressions. So what we're going to be doing is using a lot of our Algebra 1 skills, a lot of maybe our pre-algebra skills, and even adding fractions that you did back in 4th grade. So our goal here is to simplify these expressions and try to turn any fractions. We're going to get rid of any fractions. We're going to try to get rid of any operation signs, like any addition, subtraction, and try to simplify it as best as we can. So one key goal, and somebody said this sort of looks like chemistry, and it's sort of like dimensional analysis. We're going to be simplifying diagonally a lot. So remember, you probably learned it back in 4th grade when you multiplied fractions like this. Now, I know a lot of students, they didn't like to do the simplify diagonally, so instead they just multiplied. But this is where this simplification comes into play. I could simplify the 2 and the 10. 2 divided by 2 is 1, and then 10 divided by 2 is 5. And then the same thing here on the other diagonal. I could divide them both by 3, and then it makes multiplying those fractions a lot easier. We're going to be doing the same thing, but without just numbers. They're going to be the trig functions. So for example, if I have sine x over cosine x times cosine x over sine x, I can simplify diagonally here. I can make the sine x's both 1s and the cosine x's both 1s. multiply what remains. 1 times 1 on the top, 1 times 1 on the bottom, simplifies to a 1. So that's our goal here. Remember, when you do that cross simplification, it doesn't make it disappear, it turns it into a 1. So just remember that. So again, we're going to be using all different techniques. We're going to be using factoring out a GCF. We're going to be factoring trinomials, factoring the difference of two squares, adding fractions, multiplying fractions, all different things, all our Algebra 1 skills, but now they're going to have trig functions. They're going to have sine, cosine, tangent, cotangent, cosecant, and secant in the problem. So let's take a look at our first example. So my first example here is sine x cosine squared x minus sine x. So I need to find a way that I can make this turn into a single term. So at first glance, you're going to say, well, both terms have sine x in common. So that should be a clue that the way that we're going to simplify this is by factoring out a greatest common factor. And that greatest common factor is going to be sine x. So my GCF is sine x. I'm going to divide both of my terms by sine x. And then the answer to the division goes in the parentheses. So after I divide this one, I'm left with just cosine squared x. And then when I divide this one, I'm just left with 1. Because anything divided by itself is 1. Now, you're thinking, well, why did you bother doing that? It looks like you just made it worse. What we need to do here now is do a substitution. Remember your Pythagorean identities, they all involved squares. So just remember, whenever you're going to try to substitute and use a Pythagorean identity, whatever you're substituting for has to be something squared. Now this is where manipulating those Pythagorean identities is going to come into play. So what I'm going to do is I'm going to be substituting a Pythagorean identity in for this. And the Pythagorean identity that I'm going to rearrange is going to be that first one, the sine squared x plus cosine squared x equals 1. I'm going to manipulate it and solve for one of the pieces. And what I'm going to solve for is sine. But I'm going to move the 1 over. And now I have sine squared x plus cosine squared x minus 1 equals 0. If I move now the sine to the other side, now this and this look the same. So I'm going to subtract sine squared x from both sides. And now I have cosine squared x minus 1 equals negative sine squared x. So now I'm going to do a substitution. I'm going to take out this, and I'm going to replace it with what it equals, which is negative sine squared x. So now I have the red that's still there. I'm taking out what's in the parentheses and replacing that with the Pythagorean identity. And now I can multiply this, and it'll turn into a single term. So sine x times negative sine squared x becomes negative sine cubed x. Remember, when you multiply, you add exponents. So now this has been simplified, and this is your final answer. And again, these are going to take practice. Let's try the next one. We're going to do a similar scenario. We're factoring out a greatest common factor. Notice they both have in common cosecant x. That's my GCF. So after I divide this one, notice this will cancel. So I'm left with cosine squared x. And then after I divide this one, anything divided by itself is 1. Notice what's in my parentheses looks like the same thing I had before. Remember when I rearranged this Pythagorean identity, I could rearrange it and I got cosine squared x minus 1 equals negative sine squared x. So again, I'm going to do a substitution. I'm taking this out and I'm putting this in its place. So cosecant x times negative sine squared x. Now, in this particular problem, I don't want to multiply it and put it side by side. I'm going to now simplify it a bit further by replacing cosecant with its reciprocal identity. So I'm going to change this. The reciprocal of cosecant is sine. So I'm going to change this into 1 over sine x. Notice it wasn't squared, so I'm just putting a sine x. And then this one over here, negative sine squared x. I could put a 1 under it because I'm multiplying these two. Here's where your simplified diagonally comes into play. I could take away this one, make it a 1, and take away 1 out of the exponent. And then my final answer is just negative sine x. So notice here, I used a Pythagorean identity, I used a reciprocal identity, and then I divided and simplified diagonally. Okay, so these are all being multiplied. So what I can do here is, my goal is to get this to simplify down. So I'm actually gonna, notice none of these are squares. So what I need to do here is probably use my quotient identity and a reciprocal identity. So for here, I'm going to change secant into its reciprocal, which is 1 over cosine. I'm going to change cotangent into its quotient identity, which is cosine theta over sine theta. But then the sine theta I'm going to leave alone. Because again, remember, your goal here is try to get things diagonal from each other so that they'll cancel out. So notice now, with the cosines, they're diagonal from each other. So I can simplify, and these become 1s. And then I can do the same thing with the sines. And they become 1s. Now I can multiply what remains, which is just 1 times 1 times 1 in the numerator, and 1 times 1 times 1 in the denominator. 1 divided by 1 is 1. So we got that entire thing to simplify down to a 1. Now, if you noticed, they changed what represented the angle. Notice in example 1, it was sine x. Here it's secant theta. The symbol that's here after the trig word, like sine x or cosine theta, this is a variable that represents the angle. In WebAssign, you're going to see that they're going to change that. It might be sine y. It doesn't matter, it's just the variable that's standing in for the angle measure. They're even going to use other Greek letters. So I saw one question on WebAssign where they're using beta instead of theta. And that would be that, looks like a cursive slanted B. Just know that when you see those different symbols, they're just variables. So don't get confused, it doesn't change anything. All right, so let's try number 4. So again, whenever I see something squared going on, that's going to be a clue that maybe I'm going to use a Pythagorean identity. And that's what I'm going to replace in the parentheses. The cotangent, however, I'm going to replace with its quotient identity. So for the cotangent, I'm going to change this one into cosine squared x over sine squared x. Now I know on the second slide it just showed cosine over sine, but cotangent here is squared, so that's why I need to square both the cosine and the sine. Now in the parentheses, this is going to be replaced with an identity. So that identity that I'm going to use for this one is going to be tangent squared x plus 1. Now remember, addition is commutative, so the identity that we're memorizing from that second slide is this. But notice in the problem, it's got 1 plus. Remember, it doesn't matter the order you add things. So I'm going to replace this with secant squared x. And I can put a 1 here if that helps. So now what I'm going to do, I still don't have anything that's going to cancel. But if you remember that the reciprocal of secant is cosine, I can now change secant into 1 over cosine, and then I can get something diagonal to cancel. So let's leave the red one alone. And then we're going to flip this one to its reciprocal. And now I can cross simplify with the 2 cosines. And now I'm left with 1 over sine squared x. Remember, you don't want to leave anything as a fraction. So now I'm going to do the reciprocal of sine, which is going to be cosecant. And there's your final answer. Yes. Yes. Now the next part is a little bit easier if you remember how to factor. So the next 4 examples, the instructions are simplify by factoring. Pretty good on this slide? All right, so again, the instructions now, before it was just simplify, now it's by factoring. So what we can do here is think of this, pretend like this word is not here, and we could put the 2 over here on the x, and this is what we're trying to factor, the difference of 2 squares. If you recall, this difference of 2 squares will factor into x plus 1 and x minus 1. Now our final answer for simplify by factoring of the trig function here, I now need to add back in that word SEC that I had crossed off. So the final answer here is going to be secant x plus 1, secant x minus 1. Now, if you write secant x minus 1 first, and then secant x plus 1 second, it doesn't matter. Either one is acceptable. We don't take it any further. All it wanted us to do was factor the difference of 2 squares. Let's try number 6. This one's actually a trinomial that we need to factor. And again, if you want to pretend like the word tangent isn't there, what we can turn this into is 4x squared plus x minus 3. And now, I don't care what method of factoring you're going to use. You can use guess and test, you can use factor by grouping, or whatever other technique you want to use for factoring. So for here, if I do guess and test, I could try my factors of 4. They're going to go right here. So it's either going to be 2 and 2 or 4 and 1. I'm going to try 4 and 1. And then in my second spot, I'm listing the factors of -3. And there's only either 1 times -3 or -1 times +3. And again, you're going to FOIL them to figure out which one works. So if you place that in there like that, you have to do a quick FOIL, make sure it goes back to this. If it doesn't, then you got to start over and maybe put the 1 first. So if I FOIL this, I get 4x squared, 4x, -3x, and then last is -3. Notice when I add them, I do get the middle, so I picked the right factors. Now, if you don't like guess and test, you can also do factor by grouping. So let's say instead, you want to factor this by grouping. So let's rewrite the problem. Remember, you multiply the beginning and the end. And you're looking for two numbers that multiply to give you the -12, but who add to give you the 1. And then in here, you could put 4 and -3 because they both work out. So then if you factor by grouping, remember, you leave these two the same, but you're replacing this with these two numbers. So the factor by grouping goes like this. It doesn't matter which one you put first. I could put the 3x or the 4x first, but I got to put the right sign in here. And now I make my groups. Group here and a group here. GCF of first group is x. GCF of second group is 1. You put the two GCFs together. And then this thing that is written twice, you write it there. Notice it's the same answer I got when I guess and tested. So I don't care which technique you use to factor the trinomials, whether it's guess and test or factor by grouping, you can choose. So let's go ahead and now we got to put this back and add in the word tangent. So we're going to put the word tangent in front of each of these x's. So the factored trinomial becomes 4 tangent x minus 3. Fix that. And then x tangent, nope, sorry, tangent x plus 1. Now, you could have also written it like this. It doesn't matter. Either way is fine. But the -3 needs to go with the 4. And the +1 needs to go with the other 1x. So that's that trinomial factored. Let's try another one. Again, 2 terms here. So this should be a clue that these are 2 perfect squares. One's a perfect square. So again, you could think of it like this. 1 minus x squared. Just pretend like the cosine's not there. And then factor it, 1 minus x, 1 plus x. And it'll FOIL back. And then just add in the word cosine. So this becomes 1 minus cosine x and 1 plus cosine x. Again, you could have written the 1 plus first or the 1 minus. Either answer is acceptable. Try example 8, another trinomial. So again, if it's easier for you, now this is a typo here, also change this to a C. So if you want to change this and make this 2x squared minus 7x plus 6 to get your factors, and then go back and add in cosecant, you can do that. So again, you can do guess and test or factor by grouping. 2 and 6 aren't bad. You could probably do guess and test pretty quickly. Factors of 2 are just going to be 2 and 1. Factors of 6 are either 6 and 1 or 2 and 3. And both signs have to be the same. So it's going to be 2x minus 3 and x minus 2. Because they need to multiply to get a positive 6, but add to get negative 7, and it does. So now that I found the correct factors, now I can go back and put in the cosecant in front of this x. So final factors here are going to be 2 cosecant x minus 3, and then cosecant x minus 2. Two more factoring examples. This time it's a little different. We're going to need to do a substitution first, and then we can factor the trinomials. Pretty good on example 8? Okay, let's try 9 and 10. So notice the two words are not the same. In order to factor this, I need to make them both cosecant or both cotangent. However, as soon as I see I have something that's squared, this tells me I'm going to use an identity. And the identity I'm going to use and substitute is going to be 1 plus cotangent squared x equals cosecant squared x. So I can take out this and put what it equals. And then now I have a problem with all cotangents. So I'm going to combine my like terms and then put this into standard form so I can factor it. I'm going to write the cotangent squared first, then the cotangent of x, and then add 1 minus 3. Now I have a nice easy trinomial that I can factor. This will actually factor if you want to take out the cotangents so you can see it a little easier. This is the trinomial we're factoring. Factors a negative 2 that give me negative 1. And those factors are going to be negative 2 and positive 1. And then just add in cotangent in front. So it'll factor into cotangent x plus 1, cotangent x minus 2. And again, you could write it the other way. You want to write the minus 2 first, and then the plus 1 second. You can do that as well. Let's try one more example, and then we'll save the last 6 for tomorrow. Again, I will still put the last 6 in the video for anybody who wants to watch the video, but I will do 11 through 16 tomorrow. So let me try number 10. So for number 10, same scenario. I'm going to replace this secant squared x with a Pythagorean identity. And the Pythagorean identity I'm going to use is going to be tangent squared x plus 1 equals secant squared x. So I'm going to take this out, and I'm going to put this in its place. So tangent squared x plus 1, replace the rest of the problem. I'm going to combine my like terms. These are like terms, and put it in standard form. So tangent squared x plus 3 tangent x plus 2. And again, if it's easier for you to think of this as x squared plus 3x plus 2, factors of positive 2 that give you positive 3, that's going to be x plus 2 and x plus 1. And then remember to add back in the word tangent. So tangent x plus 2, tangent x plus 1. And you're done. Okay, let's try the next example. So now we're back to simplify. So now what I can do here is look to see there's no GCF that I can pull out, but I can change cotangent into its quotient identity. So I'm going to switch this. So I'm going to leave the sine x alone. I'm going to change cotangent into its reciprocal. So I'm going to make this cosine x over sine x, and then I still have the cosine. So I'm going to go ahead and multiply this, and I get cosine squared x over sine x, and then I'm still adding the sine x. So the next thing I want to do is find a common denominator. So my common denominator is actually going to be sine x. This one's already set. It has the common denominator. This one's missing it. So I'm going to multiply it to the top and the bottom. And this numerator becomes sine squared x. So now that I have a common denominator, I can add my numerators. Add the numerators. Sine squared x plus cosine squared x over sine x. Remember, this numerator right here is actually a Pythagorean identity. So if you recall, that's sine squared x. Okay, so I'm going to be using the Pythagorean identity of sine squared x plus cosine squared x equals 1. So you can see already that this right here is this, so I can replace this with a 1. So now I have 1 over sine x. Again, I don't want to leave anything as a fraction, so I'm going to use a reciprocal identity, and it's cosecant x. Let's try number 12. Again, there's no GCF that I can factor out here. So what I'm going to be using is, again, quotient identities and reciprocal identities. So I can go ahead and change cosecant into its reciprocal, which is 1 over sine x. And then I'm going to turn in the cotangent into its reciprocal. So I'm going to leave the cosine alone. And then the reciprocal of cotangent is cosine x over sine x. I can go ahead and multiply and get 1 over sine x minus cosine squared x over sine x. Notice I already have a common denominator, so I can just add my numerator. So 1 minus cosine squared x over sine x. I can again use a Pythagorean identity. I've already seen this one. So remember, here is the Pythagorean identity, the original form of it. I'm going to rearrange it and subtract cosine squared x from both sides, leaving me with sine squared x is equal to 1 minus cosine squared x. And I'm going to do a substitution. So I'll take this out and put what this equals, which is sine squared x. I still have the single sine x in the denominator. And again, I can simplify, make this a 1, take away 1 from the exponent, leaving me with just sine x. Try another one. Now this one looks a little bit more complicated. So for here, what I'm going to do is I'm going to add these two. I need to find a common denominator. My common denominator is going to be both this and this. So I'm going to write 1 plus cosine x and then sine x and the bottom for each. But I have to go back and figure out what each fraction was missing. So for the first one, notice it's missing the sign x. So I'm going to multiply that to the top and the bottom. So when I multiply the numerator, it becomes sine squared x. Over here, this one's missing the 1 plus cosine x. And here what I'm going to do is I'm going to distribute the cosine to both of these. So I get cosine x plus cosine squared x. And now what I'm going to do is, since I already have the common denominator, I can add my numerators. Now, when I go to add the numerator, I'm going to flip-flop these, and I'm going to use the commutative property. So I'm going to do sine squared x plus cosine squared x plus cosine x. And then it all has the same original denominator. Now, the reason why I use that commutative property is because I wanted to get these two terms side by side, because again, remember up here at the top, I'm going to use this Pythagorean identity again, and I'm going to replace sine squared x plus cosine squared x with a 1. So I can change this to a 1. And then now, let's see what else we can do here. Now I have cosine x plus 1. Or actually, I can write it in the same order that it was. I'm going to write 1 plus cosine x over 1 plus, let's do it in the colors that are there. So let's do it in the red. So 1 plus cosine x, and then sine x. Notice these will cancel, become 1s. So now I'm left with 1 over the sine of x. I don't want to ever leave anything as a fraction, so I'm going to use a reciprocal identity, and the final answer is cosecant x. Let's try number 14. Same thing here. I'm going to add these, so I need to find a common denominator. My common denominator is going to be both. So I'm going to have 1 plus sine x and 1 minus sine x underneath each fraction. And then 1 minus sine x. And now I need to figure out what each one was missing. So this one was missing the 1 minus sine x. Whatever you're going to put in the denominator, you do in the numerator. So this becomes 1 times 1 minus sine x. And then over here, this one's missing the 1 plus sine x. Whatever you do to the denominator, do to the numerator. And now I have a common denominator, so now I can just add my numerator. Notice when I go to add here, notice this sine x and this sine x cancel. So then I'm just left adding 1 plus 1, so I get 2 over 1 plus sine x, 1 minus sine x. I can actually FOIL that denominator, and this actually becomes 2 over 1 minus sine squared x, which again is a Pythagorean identity. Remember how we use this one again. And I know I'm writing it a lot, but again, you'll get into the habit of recognizing it right away. So again, if I solve for cosine squared x, it's 1 minus sine squared x, which is what I have here. So I'm going to replace it. with cosine squared x. And then now I'm going to use my reciprocal identity, move this to the top as secant. And you're done. Let's try 2 more examples. So notice here, what's happening is I'm actually just multiplying something by 1. So if I go ahead and just multiply this, 1 times 1 minus sine x is just 1 minus sine x. The denominators I have to FOIL, and this becomes 1 minus sine squared x. Again, I can use the same identity I just used and replace that denominator with cosine squared x. And then I have 1 minus sine x on the top. Now, what I can do here, it starts to get a little tricky. So what I can do here is pull each of these apart. And I could do 1 over cosine squared x minus sine x over cosine squared x, which then I can turn this into secant. And then this I can actually pull apart and make it sine x over cosine x, and then 1 over cosine x, and then turn this into tangent, turn this into secant, and then this one stays here. Now this time we did keep a subtraction sign. Now for the last one, what I can do here is I could replace my numerator with an identity. I could make it 1 minus sine squared x over 1 minus sine x. I'm going to factor this and make this 1 minus sine x, 1 plus sine x over 1 minus sine x. These cancel, and I'm just left with 1 plus sine x. Now, I can also multiply by its conjugate, and that's really what I was doing in the other problem. So another way to do this is, and the only time you would do this is if you multiply something by its conjugate, then the result needs to be a Pythagorean identity. So the conjugate here would be 1 plus sine x, and again, whatever you do to the denominator, do to the numerator, because essentially all I'm doing here is multiplying it by 1. So then here, what I can do is cosine squared x times 1 plus sine x, and then I can FOIL the bottom, and then this becomes 1 minus sine squared x, and then this turns into a Pythagorean identity. So then this becomes cosine squared x. The top stays the same, and then these cancel, and then I get the same answer. So you can solve these. Again, there's different ways to go about doing it. Again, at the beginning it's kind of hard because you don't know where to stop, but if you can get it down to a single term, that's your goal. So that is it for the notes on 7.1.